Now let's talk about Newton's law of viscosity and the rheology of fluids. In the last lecture, we discussed the shear stress and the shear rate. And today we are going to see how these two are related with each other. So we know that shear rate is defined by the velocity gradient. So this is the definition of shear rate. And this shear rate can be a function of space because the velocity itself can be a function of space. And it can also be a function of time. So you may wonder if the shear rate is sort of complicated profile, does the shear stress change with it or how it behaves? So it depends on the property of the fluid. The first we are going to discuss is the Newtonian fluid. The Newtonian fluid, by definition, is a type of fluid that the shear stress is proportional to its shear rate. So this equation is linearly proportional to it. This is true regardless of the value of shear rate. If you draw tau as a function of gamma dot, you will get a linear line. That is Newtonian fluid. And for any linear proportional relation, you may ask, what's the constant of proportionality? And it happens to be, this is called mu. So tau equals to mu gamma dot. The mu is nothing but the dynamic viscosity of fluid. In SI unit, the dynamic viscosity is in Pascal second. It's the same as kilogram per meter second. So this is measured in kilogram meter second system. Another popular unit is called points. We use capital P. 1 point is defined by 1 gram per centimeter per second. So it's in the gram centimeter second system. And you can convert these two. You can figure out that 1 centipoise is 0.001 Pascal second. The centipoise is just a 100th of a point, so we call it centipoise. So 1 poise is 100 centipoise. The dynamic viscosity of water at room temperature is about 0.001 Pascal second. And if you use the unit of poise or centipoise, it's just 1 centipoise. So this is also pretty popular in industry because it's just, we can say 1 centipoise. It's easy to say it compared to 0.001 Pascal second. The dynamic viscosity is the same as kinetic viscosity. In later lectures, we will discuss kinematic viscosity, which is kinetic viscosity divided by its density. But for now, let's not worry about it. Let's just look at the kinetic or the dynamic viscosity. By default, when people say fluid viscosity, they refer to the dynamic viscosity. So how do we use these to solve problems? Let's still use the two parallel plate example we discussed in the last lecture. So you have an up plate moving at a velocity v. You have a lower plate, which is stationary. And we build our coordinate system, x and y. The velocity profile of the fluid is that the x component of the fluid velocity, which we call the v subscript x, it's a function of y. It is a linear in the y direction, so it's capital V multiplied by y divided by h. So h is the distance between the two plates. So this distance is h. And to figure out the viscous shear stress in the fluid, let's just use the definition of Newtonian fluid. So the tau, which is the viscous shear stress, tau x, is the dynamic viscosity multiplied by the shear rate. This is the definition. Definition of Newtonian fluid. Then you carry on the computation. So what is gamma dot? Gamma dot is dvx dy. Then you can plug in the expression of vx. We just give you the expression, it's linear in y. So the derivative give you v divided by h. So the final viscous shear stress is mu v divided by h. So you can see it is constant in this case. Well, it won't always be a constant in other problems. Later on, we will, very soon, I think in the next lecture, we will talk about the pipe flow. And in that case, the shear stress isn't a constant. But for this laminar flow between two parallel plates, because of the linear profile of velocity, when you take a gradient, you get a constant shear rate. And a constant shear rate give you a constant shear stress if it's a Newtonian fluid. So here we have seen an example of how to use dynamic viscosity to calculate the shear stress. And you may have problems like established in different geometry. For example, you may have a pipe flow. For a pipe flow, maybe let's consider cylindrical pipe. And you may say, okay, this is my z coordinate, which is along the axle of the pipe. And then this is my radial direction. You can see you may have type of flow developed in this way. You would have your velocity along the z direction as a function of r. And in this case, your shear stress would be written as tau Rz is mu dvz dr. So dvz dr is the shear rate because the velocity varies along the y direction, along the radial direction. So you will have the viscous shear stress being developed horizontally along the z direction because there are different fluid velocity along different layers of the fluid along the y direction. So if you look from the side, so if you just look at the one end, then this is your radial direction. At any layer of fluid, different r distance to the center, you will get a different fluid velocity, and that's how the shear rate is developed, and then that's how shear stress is developed from layer to layer. So in the case of like fluid confined by two plates, you have this layer, you have velocity that momentum being transferred from layer to layer. And in the cylindrical pipe, you have velocity being the momentum being diffused or transferred from layer to layer along the radial direction. This is the one layer, two layers, third layer, etc. Okay. We will come back to this in the next slide. So this is for pipe flow. This is how you find the shear stress. Let's look at an example. Say a layer of molten oil. Let's assume Newtonian. A layer of molten oil is confined between plates being 2 millimeters apart. The top plate at a constant velocity of V equals to 0.5 meter per second, while the bottom plate is stationary. The bottom plate is stationary. If the viscosity of the oil is given, if the viscosity of the oil is mu equal to 0.25 Pascal second, find the shear stress acting on the oil. So for this problem, it's exactly the same as the parallel plate we have discussed. And we know which equation to use. So we know that from Newton's law of viscosity, Newton's law of viscosity, we know that tau equals to mu dvx dy, and this is mu dvx dy is v divided by h. So we can plug in the numbers. So tau is mu is 0.25 Pascal second multiplied by the velocity of the plate, which is 0.5 meter per second, divided by the distance between the two plates, which is 0.002 meter. It gives us 62.5 Pascal. So hopefully this simple example helps you to develop some intuitions behind these type of problems. Now let's leave a exercise, a homework problem. So water goes through a pipe at a certain radial position studio position, the velocity gradient is known to be dvz dr equals to 300 per second. If the viscosity of water is 0.001 Pascal second, find the shear stress at that point.